All right, so a couple things off the top before we jump into the material today. You can kind of see I put up the fifth and final Connect, and today after class I will put up the fifth and final Excel. Those will both be due next Friday at the end of the day. If you've done the first 4 assignments, since I dropped the lowest of each kind, essentially you don't have to do those, right? Because if you don't do them, you get a 0. What's your lowest? It gets dropped, right? If you didn't do so well on one of the assignments and you do that, essentially would kind of like replace whatever your current lowest grade is. Okay? So this is where, going all the way back to day 1, I said front loading your effort in this class kind of helps towards the end. You have a little bit less time to do these assignments than others, but right, if you've done the first 4, you don't really have to kind of be concerned with what your grade would be on these 5th ones. It would almost be more like additional kind of practice and study for that final exam. Right? Also this afternoon, I have those practice exams ready to go. I just need to get them posted this afternoon. So those will pop up there on Canvas later today. And that should be kind of take us, everything other than the final, right? That should be everything else other than the final. Once I have, we have that 5th Connect in Excel. I'll also, after today's class, kind of since the due date was when we started class today for this Learn Smart, I'll kind of take all of your Learn Smart assignments, drop your lowest one. So if you missed one, that'll get dropped, and kind of show you what that Learn Smart grade is with your lowest dropped, and kind of have that starting to be what Canvas is using to calculate your grade. All right, so I'll have that lowest drop kind of show up there as well today. I will also put an announcement up. It's hopefully I'm getting the number right. Number 7 on the 4th Connect assignment. There's a small issue with it. Instead of putting it in as a decimal, it's reading it as it wants you to put it in as a percent. So instead of like 0.02 to 0.08, it wants you to put in 2% to 8%. I don't know why it's set to be that way, but that's what it is. So I'll get an announcement up so that you don't kind of struggle with that one too much as well. Okay. Any questions from me before we kind of jump into material here today? All right. So we'll go back here. We left off. We'll go through a couple quick matched pairs examples, and then we'll dive into this next topic, which is linear regression. Okay. So we left off kind of thinking about these matched pairs examples. So here's another kind of case where we could do that, where I've got the same 40 Starbucks card holders, and I want to know what was the effect of Starbucks putting the calories on their menu, right? So I can see what these same 40 people's calorie consumption was before, and then what it was after the calorie was posted on the menu. So I do that for every single person. I calculate that difference variable. I then find the mean of that difference variable, and I find it was 2.1. I have a variance on that difference variable, 64. Sample size was 40. So if I'm writing down kind of everything that I have here, so I don't forget it. 2.1, the variance was what, 64? And if I wanted to build the 99% confidence interval, what would my alpha value be here? 99% outside would be 1% in decimal form. My alpha would just be 0.01, right? So from here, right, we would have to use that formula that we had last class, which said it really looks like just what we were doing with one population. Instead of the sample mean, we'll take that sample mean difference. We'll go a certain number of standard deviations away, but we know that we need to use that student t distribution because all we have is a sample variance. Right? So we take the sample statistic we found, we go a certain number of standard deviations above and below to get my upper and lower bound. Well, if I got to go 3 standard deviations, the actual amount that I need to go to the left and the right would be that number of standard deviations times what the standard deviation is of that statistic that I'm interested in. So really at this point, it's a matter of plugging our values in, right? We've got 2.1. Here our variance was 64, sample size was 40. The only thing left that we need to do is look up this t value. So when we're doing that, we can kind of think about, we want the t value, or the number of standard deviations away that we need to go to get alpha total outside of the interval, or alpha over 2 on each side of our interval. Well, if our alpha is 0.01, then the area that we want in our tail is 0.005. And we said, because we're looking at the same 40 Starbucks cardholders, our degrees of freedom simply goes back to being n minus 1. So 40 minus 1 here, our degrees of freedom is 39, right? So degrees of freedom of 39, the area I want in the tail is 0.005. So when I go to my t-table here, excuse me, I want 0.005 in the tail at a degrees of freedom of 39. 2.708 is that t-value. I plug that in. Now I've got everything that I need. I'll subtract my margin of error to get my lower bound, add my margin of error to get my upper bound. Okay. So if I do that, maybe, there we go. I end up with negative 1.3 and 5.53. So at the 99% level, what can I say about the change, the true change in calorie consumption here? Well, you can't really say much, right? Because some of these values are positive, which would mean that calorie consumption went up. Some of the values are negative, which would mean calorie consumption went down. In fact, one of the values in this range is 0, which would mean it didn't change at all. So I can't really say anything at the 99% level here. Now, I don't think it'll probably change enough, but why might I be able to say that calorie consumption has increased at the 90% level? So if instead of the 99% level, I wanted to build a confidence interval for the 90% level, what's going to happen to alpha? Well, that would go up to 0.1. Now alpha over 2 would be 0.05. And in order to get a larger area in this tail, I have to go a fewer number of standard deviations, right? So my t-value would be smaller. Well, if that t-value gets smaller, then I'd be adding and subtracting a smaller amount to that sample statistic. My confidence interval is going to get more narrow. So if we had, like, I think it was what negative 1.3 to 5.5, it's going to become more narrow, and potentially it'll get narrow enough to, maybe this would be like 0.5 to, I don't know, 4.5, or I don't know the exact value, right? Maybe it gets small enough to where it only has positive values. Now, like I said, I don't think that it actually works. I don't think it gets narrow enough, but that would be the general idea. That maybe with a lower level of confidence, we could actually say that difference is only positive values, which would imply that calorie consumption went up. Okay. Any questions over anything there, or want me to reiterate something? Okay with that? So I'm going through these a little bit quick. And then great meme from Napoleon Dynamite, which if you guys haven't seen that movie, you should. It's dumb, but it's, I don't know, got some great one-liners. So I used to have a good Kip impression, but I won't do that to you guys. So I've got the same example, same 40 Starbucks card holders, right? And I want to know, has calorie consumption decreased, right? That's what I want to test for. So my alternative hypothesis, that's what I want to test for, is that did this difference, right? Did it decrease? So is the difference negative, right? Is it less than 0? I'll assume the opposite is true for my null, which is that it's greater than or equal to 0. So what type of tailed test do I have here? Yeah, I've got a less than sign in the alternative hypothesis. So I've got a left-tailed test. So if we're thinking about this, when I go to look up critical values, I want the values that give me what? 0.01, 0.05, and 0.1 in the tail. I would then have my rejection regions. Now the standard normal and the student t distribution are centered at 0. So for a left-tailed test, my critical values will all be what? On the left-hand side, negative. Right? So I can use that student t distribution to look up those critical values. I'm going to look up the different alphas, or the different areas that I want in that left tail. And my degrees of freedom, remember, was what? 39, right? Just n minus 1. So I can look those up in my student t table pretty quickly. Right? So if we do that, I say, okay, here's my degrees of freedom of 39. the areas I wanted in the tail, my alpha of 0.1, 0.05, and 0.01. So 1.304, 1.685, and 2.426. Right? So I just grab those three values. Those are my three critical values, except for they're not positive, right? I know that it's going to be those exact same values, but they're all negative, right? Because it's a left-tailed test. So that t-table, right, always looks at the right side of that distribution so that it's dealing with positive values, but it's going to be those same values on the left side. It's just they'll be negative. So I've got my rejection region right away. Now, this one was a little bit tricky in that I think the next question on the slides is what's the test statistic, right? So my test statistic is always just take the sample statistic that I found, subtract the assumed true value of that population statistic, and then divide by the standard deviation of that statistic I'm interested in, which here was just the square root of the sample variance over my sample size. I've got everything I need here, right? Sample size was 40. This we're told was 64. This was 2.1. And just like the two population examples, we're always using these assumed true differences of 0 here. Okay? Or at least that's what the kind of questions I'll give you on the exam. So it's just a little bit of computation to figure out what this test statistic is. I think it's, if we enter this into our calculator, we get 1.66. Now, if I plot that against my critical values, notice it's nowhere close to my rejection region, right? I'm not even on the same side of the distribution. So I'm not going to reject at any level here. But that kind of makes sense because if we go back, what was our null and alternative hypothesis? Whoops. Well, I'm assuming that that difference is greater than or equal to 0. And I found a sample difference that supports that assumption, right? I found positive 2.1. So that actually supports my null. So why would I reject it, right? So automatically in this one, I found evidence that supported the null. I knew my rejection decision without going through any steps. Now I could go through the actual steps, right? We found that test statistic of 1.66. We plotted it against those critical values we looked up. We can see, yeah, it's not even gonna be close to that rejection region because we actually found evidence that supported the null. Okay. Any questions on that before we keep moving? So these matched pairs examples was kind of our first look at I'm looking at the same 40 Starbucks card holders. So it's like I'm doing the difference for each person. I'm kind of controlling for some of these characteristics about the individual. So the next topic and the last topic we'll go through is linear regression. And our goal is to be able to estimate the relationship between some variable X and some variable Y, but control for a bunch of other factors. Now, when we start out, we won't be able to do that. We'll be doing some simple linear regression today. But then on Friday, we'll kind of talk about how do we control for these other factors. So matched pairs was starting to move that way. Linear regression allows us to get even closer to controlling for other factors. So we already did this last class in Excel. So we've been doing a lot of hypothesis testing, and we've done it for two populations, and we're interested in the difference between two groups. But we can also do hypothesis testing for any statistic, any sample statistic we have. So we could do it for the sample correlation coefficient. We could do it for the sample covariance. And this was kind of telling us, right, the correlation coefficient and the covariance were telling us the relationship between X and Y, right? And we said that if these correlation coefficients or covariances were positive, that told us that as X went up, so did Y. If they were negative, as X goes up, Y tends to go down. And if it was pretty much 0, as X goes up, Y doesn't really change at all, or at least not systematically with X increasing. So what if we wanted to do some hypothesis testing for these correlation coefficients and covariances? Well, we actually won't quite do that, but we're going to come up with an even better measure of the relationship between two variables, and then we'll do some hypothesis testing with those sample statistics. So we've got this relationship between this X and Y variable. We want to know, as X goes up, what happens to Y? Well, we can do that. Basically, we can plot that using a simple linear equation, right? The equation for a line. I think in math, you just what? Y equals mx plus b. Here, we're just going to use slightly different, we're going to call the intercept A, and we're still going to call that slope B. And we've got that relationship between our X and our Y variables. So what we're going to do with linear regression, to give you a little bit of an idea of what we're doing behind the scenes, or what Excel will be doing behind the scenes, because I'll show you today how Excel can do this pretty quickly for us. Let's think maybe I've got my X variable is hours studied, and my Y variable is someone's exam score, right? And I've got maybe some data set where I've got all this self-reported hours studied and what the person's exam score was. I then go through and I just start plotting every single observation or every single person, right? So maybe someone, studied 4 hours and got a, 72, something like that, right? So I plot that point. I then go through and do that for every single person that I have in this data set. I'll probably go even more, but let's just say we got a small data set here. So I plotted every single person. What we're going to be doing with linear regression is coming up with, excuse me, a line that best fits that data, right? I think you probably heard, I don't know, I feel like there's like high school science or something, you can talk about this stuff. Like I remember like on some standardized tests, right? You've got all this data plotted, draw a line that best fits that data. That line will tell you kind of the relationship between that X and Y variable. So we've got a line. It's going to have some intercept A, right? And if we did rise over run, we could figure out what that slope B is. Right? So once I plot this line of best fit, I could figure out what its intercept and what its slope are. Now, another way of thinking about this, so we've got this equation now where Y is a function of this X variable, right? Or our exam score is a function of the hours studied. So I could plug in different values for X. So I plug in X is equal to 2 here. When I actually have the numbers or the values for the intercept and the slope, I could then come up with what we'll call predicted Y values, right? So if I plug different values of X into this equation, once I have the values for A and B, I can come up with predictions for what Y will be, right? So all these points on this line are the predicted Y values for different values of X, right? Or the predicted exam score for different hours studied. Another way to think about the slope is if I go up by 1 unit, right? X goes up by 1. Well, how much does Y change by? Well, the intercept stays the same. If this goes up by 1 unit, it would just be adding B into that predicted Y value one more time. So X going up by 1 unit, the slope is essentially telling us how much does that predicted Y value change or go up from a 1 unit increase in X, right? That's what the slope of a line tells us, that if X goes up by 1, that slope is how much the Y value would increase by. If it's positive, if the slope is negative, then it's how much it goes down by. Same idea. Okay. Any questions over this idea so far? Okay. So we can come up with these predictions for Y, but notice, like, let's say I look at this one right here. Maybe I don't know, it will say this is 5 for X, right? Well, I can come up with my predicted Y value, but the actual Y value, right, the data point, someone who did study 5 hours was down here. So the difference between that predicted and the actual Y value, right, we're going to call that difference the error, or epsilon, right? And kind of using the Greek letter to represent that. So the difference between our predictions and the actual Y values, that will be what we call our error term. That's how far off we were for that one observation. Okay. So we can come up with these predictions based off this line of best fit, but we're going to make some errors, right? We're going to be a little bit off for every single observation. But on average, right, we're going to be pretty close. Okay. So, let's see here. Let's skip ahead a little bit. I'll show you on here. So we're making these errors, right? And sometimes, you know, the line of best fit is going to be generally pretty good, right? Our errors are pretty small here. But occasionally we do have some outliers. Like maybe here's someone who, you know, was just a genius. So they didn't study very much, but they got a really good exam score. Well, I mean, that would be a huge error if we try to predict that person's exam score by just using their hours study. Because we don't have all the characteristics that, you know, like what their intellectual ability is, like, so we haven't factored in any other information here, just hours studied. So we'll make errors and sometimes they'll be relatively large. Right? So how can we get this line of best fit so that we're going to minimize those errors? Right? That's what we'll eventually get to. But we can think about some terms that we're going to need before we get too far into this. So the first is going to be this y variable on our left-hand side, we'll call our dependent variable. It depends on x, right? It's a function. Y is a function of x. It depends on x. We'll then call x, or our right-hand side variable, our independent variable. It's what's changing on its own. So independently, x is changing. And then as a result, because y depends on x, it will also change. Right? As someone studies more, their exam score will change. We're then going to use this idea of regression analysis, which is, you know, this built-in tool. Now, there is an actual equation to it, like Excel will do it behind the scenes for us, but there is an actual equation, which we'll look at today, that will give us the estimates for what that intercept and what that slope are. So I'm calling them estimates because once we come up with this line of best fit, well, the intercept and slope values for that line are based off of sample data. So they're really kind of like sample means or sample proportions. They're just estimates based off sample data of what the true slope and intercept value is. But, you know, if we have a large enough data set, hopefully these predictions will be pretty close. So we'll have this kind of predicted intercept and slope value based off this line of best fit. And, you know, I kind of already went through this, but right, we've got our intercept, we've got our slope. We could have no relationship exist. You know, maybe we have a data set where that slope is 0. Right? Maybe we have a positive relationship. That was like the one that we looked at before, where B is going to be positive. If I had data that looked like this, the line of best fit is downward sloping. So I know that as X goes up, Y is going down. So there my slope would be negative, right? Or B would be less than 0. And we won't do this in this class, but if you want to kind of push this further, you start getting interested in things, you want to take another stats course, right? You can estimate relationships that aren't linear. We know that not all relationships are linear, right? The first hour you study is going to be a lot more valuable by the time you get to the 20th hour. I mean, you either know it or you don't at that point, right? And so we probably know there isn't a linear relationship there, but we could estimate that as well using linear regression. We won't do it in this class, but you could estimate these types of relationships. Okay. So what are we trying to do? So I said that we were making errors when we make our prediction. So our predictions were just based off of these estimates that we found for the intercept and the slope. So when we were predicting y, well, we were just using these values that we found from our line of best fit and plugging in different values for x, right? Well, for any one person, when we come up with that prediction, we said the actual y value will be off a little bit. So the actual y value will include what we call this error term, right? And, you know, this is the idea of, you know, maybe I'm trying to do like years of education as my x variable and income as my y variable. If I estimate that relationship and then I try to predict what Bill Gates's or, you know, Elon Musk's income is just based off of their, you know, years of education, I'm going to be way off, right? So every person is going to have their own individual error term. Okay? Or every, say person in that example, but every observation will have its own error term. So if we think about this predicted y value, the actual y value would just be the predicted y value plus this error term, or plus epsilon. Okay? So let's skip through. We already kind of looked at this. I drew this out for you, right? Sometimes our errors, we're going to make predictions that are too low. Sometimes we'll have predictions that are too high. So we're going to have like positive and negative error terms, right? Depending on if our prediction is too low for the actual Y value, then the error term is positive. If our prediction is too high, well, then the error term is going to be negative. So the goal of choosing this line of best fit is to somehow minimize all these errors that I'm making. I want to draw a line through this data where I've minimized the total errors or the sum of the errors. Okay? But there's a couple problems with that. If I try to minimize the sum of all the errors, and some of my errors are positive, some are negative, when I add those together, it's going to look like they cancel out and I'm not making any errors at all. So maybe we want to take the absolute value or something like that. But what we're actually going to do, oops, and I'm going to skip ahead because I duplicated the slides because I tried to add to them and make them better. So what I'm eventually going to do is I'm going to minimize the sum of all those errors I'm making, but I'm going to square those errors, right? So the error term was just the actual Y minus the predicted Y. So by squaring these errors, now if I made a positive error, positive times a positive is positive. If I made a negative error, negative times a negative is positive. So I've kind of dealt with the fact that, okay, now it doesn't matter what direction I was off, all errors in either direction are treated the same. If I was 2 below or 2 above, by squaring that error, those are treated exactly the same. We go back to the variance discussion we had also. When we square a difference here, what do we say with the variance that kind of over penalizes? We think about if I was off by 1, my error term was 1. 1 squared is 1. So we get a 1 would be added here to the sum of the squared errors. But if I'm 10 off, 10 squared is 100. So by squaring this, we not only deal with this, concern that we don't care which direction we're off by, but it also over penalizes really bad errors. Right? So we're going to minimize the sum of all these errors squared, which, how do we come up with a predicted Y value? Well, we have an equation for that, right? It was just our simple linear equation. So we're going to minimize this function. So what we could do, I don't know, you guys have to take like brief calculus or whatever, but we could take a derivative of this function in respect to the two things that we're trying to figure out the value of. A and B, our intercept and our slope. If we take a derivative of this function in respect to those two things, set them equal to 0, 2 equations, 2 unknowns, it's just some algebra. Now, it's not fun algebra, right? But eventually we can get to a point where I can actually come up with an equation that solves for what that optimal B value is, or what that optimal slope value would be, to minimize the sum of my squared errors. Or essentially, what slope value gives me this line of best fit. Okay. So I'm not going to make you guys do that, but if we did it, right, and we did all the algebra and solved, we could actually come up with an equation for that slope and an equation for that intercept based off of the data, right? The X and the Y values that we see in the actual data. Now, we're not going to do this by hand, but you can kind of imagine if I had 2 variables in Excel, I could create another column where I took the X value for every observation and subtracted the mean of X. I then could take another column and I would take every Y value and subtract the mean of Y. Then another column where I multiply those 2 things by each other and then equal sum, add them all up. Right? So you can imagine how I could probably do this function in Excel, but we've got these built-in packages that will basically do it all for us. So we'll eventually see some Excel output today. I'm not, here where I said it's a lot less computation once we get to linear regression because nobody's doing this by hand. I mean, no one's doing this by hand, right? And so they used to, which would have been terrible, but Excel will do all of this for us. So we're going to be more focused on how do we interpret the output that Excel is giving us, or what is what are we seeing from Excel here? What does this mean? So there's another version of it. We're not going to use it, so I'm not going to be overly concerned with it. If we have a little bit of extra time Friday, I might show you how you could, if you couldn't use Excel's built-in function, how you could do it step by step. And that's kind of what this slide is for. But like I said, I'm not going to make you do this step by step. We'll kind of use this built-in function in Excel, which I will show you now. So here, I've got kind of a summary, but I'll walk through this with you. So I have this two population hypothesis test. This is just the Excel file that we've been using. I'm just going to use it to have some data to work with, and we'll go to this female data worksheet. I'm going to zoom in a little bit so you can see what we're doing. So if I go to my data tab, I have this data analysis option. You may not, right? Whatever computer you're using, you may not see this, right? But how you can add this in is for a PC, and I'll try to kind of go between PC and Mac here. You'll go to File and then Options. Now, if you're on a Mac, I believe at the top when you have Excel open, there'll be like a tab that just says Tools. I don't think it's actually part of Excel. I think it's like I don't know, more of your toolbar in general on your Mac. So instead of File Options on a Mac, you should select, I think, Tools at the top there. You then should see an option down a little bit that says Add-ins, right? Or Excel add-ins. So we'll click on add-ins. We want to manage those add-ins and make sure that we have this analysis tool pack selected. Once I have that analysis tool pack selected, I'll hit OK. And now that should show up under this data tab Excel. Okay. So File, Options. I believe there's like a Tools at the top of your toolbar and on a Mac. You'll then see where the add-ins is a little bit down further on the Mac, or here on a PC, it's over here on the left side. Manage your add-ins and make sure that analysis tool pack is selected. Okay. Is anybody following on a Mac? Are you kind of seeing it where that's at? Nobody? All right, well, hopefully you can find it. I'm trying to walk through for a reason. But anyway, so you want to get that analysis tool pack worked in. If you've got like a really old Mac, there's some issues, but I haven't had that happen in the last couple of years. Like you have to go back to have like a 2008 or 2009 Mac. You have to download a program. But all the new ones, you should be able to kind of, like I said, Tools and then manage your add-ins, make sure that analysis tool pack is selected. Okay. So now that I've got this data analysis tab, I'm going to think about, if I select data analysis, I can go to regression here. It's all the way at the bottom. And I kind of cheated because I did this for the last time. So I'm going to get rid of all this. So maybe I want to estimate the relationship between height and weight, right? So I think that, if I know someone's height, I can come up with a fairly good prediction for what their weight is. So my Y variable, what I'm trying to predict, is going to be an individual's weight. Okay, so I select that weight cell, Control Shift or Command Shift on a Mac, hit the down arrow. Okay. So that selects my Y variable. I'm then going to go back and I want to select my X variable. So I'll unfortunately scroll all the way up here. My X variable I was going to use was height. Right? So Control Shift, Command Shift on a Mac, hit the down arrow. I've now got my X and Y variables selected. Now, I don't think it always defaults to this. So, oops. If the labels wasn't selected and I try to run this, it's going to get mad at me because I can't do a regression with words. Right? I need numbers here. So, oh yeah, I forgot. I selected the labels. So if I select labels here, it treats that very first cell. This is just the name of the variable, right? It's not part of the data. I then hit OK, and it'll put this on a different worksheet. Right? So what is all this output? So today we're just going to kind of focus on these coefficients, right? So coefficients are just a fancy word for this is the estimate that we have for what this intercept and this slope are. So we'll often call this my intercept or my constant is another term we'll use, the intercept or constant coefficient. And then here is the slope coefficient, right? How much that Y value is going to change when our X variable goes up by 1 unit. So if I'm thinking about here, if I have my X variable was height, my Y variable was weight. So I'm trying to come up with predictions for weight based off of these slope coefficients, right? Or these sample estimates for what the true intercept and slope are, right? These values we are seeing from Excel, they're almost like sample means or sample proportions. They're just estimates based off of sample data. So, maybe I've got a bunch of data here right? Scatter plot. And I want to come up with this line of best fit. And my X variable here was the individual's height. So Excel just told me these values. I think they were like, well, let's check. -46 about, and 3.4 was my slope coefficient. So -45 was this intercept value, and then this was about, what, 3.4? So this might seem weird, but we can start to think about how we interpret those two values. So I'll have this line of best fit. This is kind of weird here, but my intercept value is where I hit that y-axis with this line. Or another way of thinking about this is, so this was -45. It's the predicted weight when my X variable is equal to 0. So my intercept, one way we can interpret it, is this is the predicted value of my Y variable, or the predicted weight, when someone is 0 inches tall. So it's gonna have wacky interpretations, but it's just where the line starts. The reason why we get some wacky interpretations is because we never actually make predictions for people who are 0, 1, 2 inches tall. The people that we're making predictions for what their weight are, right? 60 inches, 72 inches, right? All of our data is very far from that y-axis. But when you come up with a line, like, you know, it has to start somewhere. Even if you don't actually see that in real life, this line, if we were to go back, the linear relationship would put our intercept down at this -45 value. So the way that we always interpret the intercept is, it's the predicted Y value when X is equal to 0. And that kind of makes sense, right? Because if X is equal to 0 here, 0 times anything is 0, our predicted weight would just be whatever the intercept is. Now for our slope, how do we think about using that? Well, remember the slope was just the increase. Oops. So let's see, we had like, I don't know, 64 to 65. The slope is always the change in Y from a 1 unit increase in X. So that's our general interpretation for every example. Our slope coefficient is the predicted change in our Y value from a 1 unit change in X. Okay. So here, if someone's 1 inch taller, we would predict their weight goes up by 3.4 pounds. Okay. Now, obviously, we've estimated a very naive relationship here. We haven't controlled for anything, right? There's a lot of other factors that would influence weight other than just height. But we've got to walk before we can run. This is where we're starting out. Okay? And things don't get a whole lot more complicated after this, but we understand the basic simple linear regression. The next step, which is multiple linear regression, really isn't that much more difficult. In fact, in some ways it's easier, I think. So like I said, we're not doing a lot of computation here. It's more of interpreting this output that we're getting from Excel. Okay. Any questions on this before we keep moving here? All right, so let's go back to the slides here. So a very, I guess, I don't know, relevant example on today. I've got these two variables in this survey data that I had. One was income and one was the number of days someone used marijuana each month, right? So just so happened that this fell on today. So that was like a, I don't know, cosmic or something. But I had all this data, so 5,000 observations. And so self-reported marijuana use, number of days each month, and then that individual's income. So maybe I want to come up with, estimate the relationship between, well, how does marijuana usage influence income? So I'm thinking about my Y variable, the thing I'm trying to predict is income, and what am I using to predict it, or what am I trying to figure out the relationship between income and kind of the number of days someone used marijuana each month. So if I had this data in Excel, I use that data analysis tab, I select my income variable as my Y variable, I would select the number of days someone used marijuana each month as my X variable, make sure I select the labels, right? And then hit OK, and I would get all this regression output. So I did that, but I didn't use Excel, I used another statistical program. So I'll 90% of the time try to show you, well, on the exam, I'll always give it to you as Excel output. But occasionally in classes, we're working through these examples the last week and a half here. I'll sometimes show you output from other statistical programs as well, just so you get an idea that, you know, if you saw it somewhere else, you could still interpret it. So here it's just going to say, okay, I'm going to run a regression where my Y variable is income, my X variable was the number of days someone used marijuana each month. It's a little bit older data, and the survey data goes back, I think, even to the 80s. So the numbers are going to be a little bit low when we're thinking about income here, but that's okay. So it gives me all this output, right? Number of observations. It tells me a bunch of other stuff we don't even know what it means yet, which is fine. We're not even going to use everything here. We're today just going to focus on these coefficient estimates. So my constant or my intercept, right? Those are two terms that are often kind of interchangeable. Tells me, we said, how do we interpret that? Well, that was the predicted Y value when my X variable was 0, right? If X is 0 here, then the only thing left is my intercept, right? And that's the predicted value for my Y variable, income. So the predicted income of someone who uses marijuana 0 days a month was about $32,000, based off of this sample. Excuse me. So how do I interpret then the slope coefficient? Well, we said it was always, if the X variable goes up by 1 unit, our slope coefficient tells us the predicted change in our Y variable. So if the number of days someone uses marijuana each month goes up by 1 day, right? That's our unit now. Before, with height, it was 1 inch, right? If this was, age, it'd be if I get 1 year older, right? It's whatever the unit of that X variable is. So if someone uses marijuana 1 more day a month, we would predict that their income goes down by $253. Okay? So that's how we would make those interpretations. And I think I have that written out here, both of those interpretations. And we kind of worked through that height and weight example. But we're going to start making these interpretations of our coefficients in every example that we look through. This will be something that I will ask you questions about in the exam, give you some output, give me the interpretation of the slope coefficient. And the general format, it's always, if the X variable goes up by 1 unit, the units will change depending on the variable, right? What inches, pounds, whatever it is. The slope coefficient tells us the predicted change in our Y variable from a 1 unit increase in that X variable. Okay. And you can think about, now that I've got these values, negative 253 and about 32,000. So these won't be precise. But now we could think about, I can come up with predicted income values. So my intercept was about 32,000. My slope coefficient was about 253. So now I could plug in different hypothetical values for the number of days someone uses marijuana each month and tell you what their predicted income was. Okay. So I can come up with actual predictions using these two values, just plugging in hypothetical values for that X variable. Now, this is very naive, right? Because there's a lot of other things that influence income more than just the number of days someone uses marijuana each month, right? In fact, I would argue this is pretty far down the list, right? Things like occupation, right? Probably matter a lot. Age, experience. There's a lot of other factors that probably would help us make better predictions about what someone's income is. So we want to be able to estimate the relationship between an X and a Y variable, but we also want to account for all the other things that matter. So next class, I'll kind of walk through, how do I include other variables on this right-hand side as well? Because if I'm trying to predict income, I want to make sure that I'm factoring in the person's age. I want to factor in what their occupation was. So there's a way we can do that, which is not simple linear regression, but multiple linear regression. So we'll talk about that a little bit next class, as well as if we looked at that Excel output. So we interpreted these coefficients, but there's a lot of other stuff here as well. So you'll notice there's something called like the standard error. Essentially what the standard error is, just like when we had a sample mean, we could calculate the standard deviation of that sample mean. And if we had a sample proportion, we calculated the standard deviation of those sample proportions. The standard error is essentially the standard deviation of these sample coefficients, right? So I can calculate things like test statistics. I can then look up things like p-values. but we don't have to do this by hand. Excel will do all of this for us. So really what we're going to focus on is interpreting these coefficients, realizing that they're sample coefficients. They're just like a sample mean. So we can turn them into test statistics and find p-values. Well, we're getting pretty familiar with p-values. Go out on a limb and guess that. We can do some hypothesis testing, right? Now, we're not going to have to be as concerned with identifying the null alternative, looking up the p-value. We're always going to have the p-value given to us from Excel, and really it just becomes a simple check of, is that p-value less than alpha, right? So we can skip all the intermediate steps like we had to do before. Excel will give us the p-value, and we can start to say, okay, I've got this sample coefficient, but can I say it's different from 0, right? Can I say that it's different from 3 or 4? Well, we won't do the other ones. All we're going to focus on is it different from 0? And there we'll just say, okay, check to see, is that p-value less than alpha? So we'll talk a little bit more about kind of the p-values, how we use them to make statements about the coefficients, and also look at multiple linear regression. And we'll look at an example in Excel. We talk about omitted variables. I think we'll probably start that. We might not finish it until Monday, but all that'll be on Friday, okay? So any questions for me before we get out of here today? A little bit early. All right, enjoy the rest of your day. Hopefully not too many activities.